Hi, this is Owen Astrachan for Compsci 201, Spring 2026, with a lecture for February 2nd, Big O, P1, the Markov generation assignment. Today is G Day. G is for Git, the quintessential version control used by millions of developers everywhere. G is also for GNU. GNU's not Unix. It's a self-referential acronym, free software similar to Linux. G is also for Google, arguably the OG disruptive innovation, changing the landscape of everything, well before AI pretended to be. This week in 201, there are APTs due on Thursday. We'll see one of them today, WOTO style. You already know all the APIs and concepts that you need to do these. P1 early engagement. Please see the P1 assignment. You have until tomorrow, Tuesday, February 3rd, to complete the early engagement. Code and analysis due next week, and you will likely want to get a good head start, if not finish on that, because there's a midterm on Wednesday, and the midterm will include P1 concepts. As a reminder, if you see the syllabus, you'll see that you get 6 helper sheets. That's 3 front and back, 6 total. And if you miss the midterm, it will be replaced by the corresponding part of the final. And in general, if you don't do well on any midterm, but in fact do better on the corresponding part of the final exam, that part of the final exam will replace your midterm. So there's no need to stint. Please feel free to do that, aka the incapacitation form, because it does let us know that you're not feeling well and we would like to follow up, but it doesn't give you an excuse. You take the midterm on Wednesday. If you have an accommodation, you take it as you will be arranged, but you must take it Wednesday or the final will replace it. The concepts that we've talked about last week and will continue this week include Big O, also known as O notation, which allows us to move from an empirical analysis of performance to a formal analysis using mathematics. We'll also talk about the background for P1, inheritance, and the override that you use. For example, we've seen that when you print an object, that object's toString method is actually called. You, the developer, don't call it. The println method in system.out calls it. Similarly, for hset.contains, what's called? Well, we've seen that .equals is called, and .hashcode if hset is a hash set. If hset was a poorly named array list, just .equals would be called. Again, you will override those to implement them, as you saw, for example, in Person 201, and as you'll see in later programs and projects. Just some reorienting around runtime. Here is counting the unique words in an array. Let's assume that there are n words in the parameter list. Then lines 8, 9, and 10 are the bulk of the runtime performance of this code. Now, uni.contains runs in order n time, or order u time if u is the number of unique words, because we can see that if a word has already been seen before, it's not added to the set. So only the first time a word is seen from the array list is it added to the array list uni. It's uni for unique. And as uni gets more and more elements added to it, as its size increases, its runtime also increases, because every element must be examined to see if it's equal to the parameter s to contains. Now, total plus gets 1, that is order 1 time. Incrementing a variable by 1 doesn't depend on the value, and it certainly doesn't depend on the number of elements in uni, the array list. Uni.add is also constant time, because we have seen that adding an element to the end of an array list is amortized constant time, amortized because we've seen that it's possible that the internal array may double, but over many, many additions, the average or amortized runtime is in fact constant time. It does not depend on the size of the array list. If we make one small change so that when we look at this code, we'll see something a little bit different on the next slide. But on this slide, we're going to look at the number of unique strings. So if that's U, then the first time through the outer loop, line 7, uni, the array list, will contain no elements. So it will be constant time to see if an element's in it. Then the next time a unique element is added, it will have 2 elements, then 3 elements, then 4 elements. Each time uni grows, the time for uni.contains to execute will also grow. So over all the times that uni.contains is executed, and that will be at least U times if there are U unique words, we can see that because the sum of the numbers from 1 to U are U times U plus 1 over 2, which is order U squared, quadratic runtime. And as we have seen and will see again, quadratic runtime does not scale. Now, if all the words were the same, if every word in the parameter list was the same, uni would only ever have 1 element in it. And in that case, the total runtime for the code you see here would be order n, because we still have to look at all n elements of list, but uni only contains 1. So the inner loop there inside uni.contains will always execute in constant time. Now, if all the words are different, then U is equal to n, and the runtime will be n squared, because as uni grows, 1 plus 2 plus 3 up to n, that will be quadratic in n, or order n squared. Now, we'll make one small change to this code. We make the left-hand side of the assignment statement collection. It was array list. Now, array list is a collection, so this code still runs. Uni is just a pointer, and as the code executes, uni is a pointer or reference to an array list. So it's the ArrayList.contains method that is executed on line 8. The code is still quadratic. But if we make a small change on line 5, we make uni point at a hash set, which is also a collection, then all the code inside the loop, uni.contains, is constant time. Total plus 1 constant, uni.add constant. So because uni now points at a hash set, this code executes in order n time. One small change, which is why using collection on the left-hand side allows us to make changes to the code and not have to change it everywhere. As a reminder, big O is a family of essentially equations. So here we see linear equations. That's order n, linear in x. And the second family of equations is order n squared. We don't care about the low order terms, and we don't care about the coefficient in front of the x squared in this family or the x in the earlier. That's the intuition, that all these are either lines with different slopes and intercepts or quadratics with different shapes. And in the limit, they all look the same, as we will see formally, but we want to talk about the intuition. As we saw last time, Chuck Van Loan said, if you do the formalism first, it is rigor mortis. You will not be happy. Maybe you will be so unhappy that you'll undergo rigor mortis. But if you build the intuition first, it is rigors mortis. The foundation of rigor is built on intuition, and then you introduce the formalism. Here, for example, is a step towards the formalism for big O. What we're going to be interested in is the limit. And you can see here a Wikipedia reference, and it says f of x is order g of x if there's a constant c and an x naught, an x0, such that f of x is less than or equal to c of g of x whenever x is greater than x0. Now, rather than go through this formally, which you will do in later courses should you continue with computer science, I'd like to look at the formal definition for continuity. What does it mean for a function to be continuous at a point P? The intuition is you can draw it without picking up your pencil. The formal mathematical definition is for all epsilon greater than 0, there's a delta greater than 0, such that if p minus x is less than delta, then p minus f of x is less than epsilon. The intuition there is that if you have a neighborhood around f of x, then there's also a neighborhood around x that maps to that. Do you need to know this formal definition to understand continuity intuitively? I don't think so. Do you need to know that this is the formal definition for big O? What does it mean that T of n is order G of n? It means that in the limit as n goes to infinity, T of n over G of n is less than or equal to some constant C. So to formally prove that, you'd have to find the constant. You'd have to show the limit. What it really means is we can just group all quadratics the same. And it is an upper bound, as we will see in more detail. Now, I talked about this in class last time, just to remind you that on a today computer that executes 1 billion instructions a second, a log or a linear or an n log n algorithm is pretty fast. You can see at the bottom, for an input size of 1 billion, it takes a minute for n log n, a second for n, but 31.8 years for n squared. That does not scale. We are not waiting that long. If your input is small, say 1,000 or 10,000, n squared is fine. You don't need to worry about efficiency until the size of the data that you're executing your algorithm on gets large. Here's some practice. And this is the kind of practice that you'll see on the midterm, and that we'll practice more with WOTOs. What is the runtime of calling stuff of n? And we also want to know what's the value returned by stuff of n. And when we say big O, that means you don't have to have it exact. So if you say linear, that's order n. Quadratic, n squared. Now we look at this code and we see that there's a loop from lines 9 to 11. Now, inside that loop, it's constant time. Incrementing sum by n doesn't depend on sum, and it doesn't depend on n. The value changes, but the time to execute does not change. So this loop that executes n times from 0 up to but not including n is an order n loop. So the runtime is every statement. Line 8, the loop, the return. Well, the loop executes n times, so this is an order n algorithm. Its runtime is order n. What about the value returned? We can see that sum is initialized to 0, and then it's incremented by n every time. Now, if incrementing by n is something that you find harder to reason about, then just pick a value for n, like 5. And if this loop executes 5 times, sum will be 25, because 5 is added to sum 5 times. In general, if n is added to sum n times, the value returned will be n squared. That's order n squared. And you reason about that by writing down on a piece of paper all the steps and looking at the value for sum. Let's look at another one. Here's a function parallel, and we can see it has 2 loops. Now, each loop is linear. It's order n. So the first loop executes n times. The statement inside the loop is constant time. This loop executes n times. The statement inside the loop is constant time. That means each loop is order n. So we have n for the first loop, n for the second loop. That's 2n. But 2n is still linear, so the overall runtime is order n. It's linear in n. One more. Here is a loop that you have to be careful when you examine, because the loop on line 145 starts at 1, goes up to n, but it multiplies k times 2. So the value of k starts at 1, then it's 2, then 4, then 8, then 16. And we can see that the loop executes log n times. You can reason about that, because how many times can you multiply a number by 2 until you get to n? That answer is log n. So the loop is order log n. You can also see that by just writing down, as we can see on this slide, 1 plus 2 plus 4 plus 8 plus 16. That executes 1, 2, 3, 4, 5 times. That's the log of 16 is 4. That's 4 plus 1, log n. Now the value returned is we're adding up all these numbers k. We're adding up 1 plus 2 plus 4 plus 8 plus, in this particular case on the slide we see 16, that's 31. As we've seen before, if you add up powers of 2, you get one less than the next power of 2. So the value returned will be order m, where m is a power of 2. In general, we get to use the letter that we want. We could have said it's order n, where n is the parameter. So the runtime is log n. The value returned is order n, or order m, where it's a power of 2. Here's a WOTO. Please put the video on pause, answer the WOTO, and then we'll continue.